schemes. Hopefully, maybe we may have one more visit. Yeah.
I hope to come again.
Yeah, and kind of close up the story. Yeah. Yeah. Okay. Thank you very much.
So again, I'm happy to be here again, and I thank CMI for its hospitality. So I will continue the lectures of last August. So the previous lectures were centered on groups of multiplicative type, and of which the connected one as a tori. But the ultimate goal is to understand reductive groups over an arbitrary base. And the critical tool to achieve this is to study maximal tori inside a general reductive group. And an important thing is to look at the centralizer of a maximal torus inside a reductive group. So I will start with some generalities about centralizers. And so I've prepared the lectures, which is lecture 11, and so the notes are already on the web page. But I will not start with this because it's a bit technical. I will just give from this lecture the small part of it we need for the sequel, and I will move to lecture 12, and I will give the proof of the results of lecture 11 the next time. Okay, so let's G be a group scheme and be S group scheme, and U subscheme of G, not necessarily a subgroup. So we introduce the following definition. So the centralizer of U inside G is the subgroup functor of G defined as follows for every S scheme T, the t-value point of the centralizer. So these are those J in G of T, such that GU is equal to UJ for all U in U of T. Okay, so this is a subfunctor of G, and it need not be, in general, it need not be representable by a scheme, or well, it's a subgroup functor. In general, it may not be representable by a subgroup scheme. But okay, so in the notes to be put, well, which are already on the web actually. So this is number 26.7. But we have the following result. We have the following proposition. So assume G is smooth, affine S group team and H is a subgroup scheme of G, which is of multiplicative type. Okay, so MT means multiplicative type. Then the centralizer of H is represented by a closed subgroup scheme. Subgroup scheme C of G, which is affine. Well, affine is not difficult because it's a closed subgroup in G, which is affine and smooth. So it is representable by a smooth subgroup scheme. And further, one has the following result that will be useful later. So the Lie algebra of C is given by the set of H invariants in the Lie algebra of G. Okay. So this is H invariance. Okay. So we take this for granted for the moment, and using this, we are going to move to lecture 12. And whose title is Cartan subgroups and reductive center. And so the goal is the following theorem. Which is due to Grothendieck. So let G be smooth, affine group field over an infinite okay. Then there exists a maximal torus. So I realized that I forgot to give the definition of, well, I forgot, well, yeah, I think I gave it already, but let me just recall. So over an algebraically closed field K, all maximal tori of GK, I conjugate, under the group of K points. And so in particular, all have the same dimension. And this dimension is called the reductive rank. So reductive rank of T. And one says a subgroup T of G. So now we are back to a K subgroup T of G is called a maximal torus of G. Well, if it is a torus, well, actually this is contained in the next sentence, but if T is a maximal torus of G, what? Okay, so the question of so the existence of a maximal torus is not at all obvious. So this means that over the small field, there exists a K subgroup of the right dimension, so which become by extension of scalars a maximal torus over the algebraic closure of K. But it's not at all obvious that such a torus exists, and so the goal is ultimately to prove this theorem, and then to extend it to a more general base. Okay. So just a word. So actually, in SGH3, this is proof for an arbitrary field, including the case of a finite field. But the proof has to be different for finite field. So for the sake of simplicity, I work over an infinite field. But actually, there is no restriction at all over. Yeah, one say a K subgroup T. Hmm? Yeah. You see here, K is K. Yeah, thank you. Okay, and so the argument of Grothendieck uses the following definition. So in this paragraph, so in this paragraph only, assume K is an algebraically closed, but this is for this paragraph only. And so there is following definition. Well, water. So first we define what are Cartan subgroups. Cartan subgroups over an algebraically closed field. So let P be the maximal torus of T, and let is denoted by C of T, the centralizer in G of T, so which by the previous proposition is a closed smooth subgroup of, and it is called the Cartan subgroup. Cartan subgroup associated with. Okay, so over an algebraically closed field, a Cartan subgroup by definition is the centralizer of a maximal torus. And of course, then T is a maximal torus of C of T, because C of T is a subgroup of G, so as T is maximal in G, it has to be maximal in this one. Furthermore, it is central, because this one is a centralizer of T. Hence, it is the unique, hence is the unique maximal torus of C of T, since all are conjugates. Okay, so another maximal torus is conjugate to that one, which is central, so they are identical. And now there is a proposition coming from the classical theory. And so one can see the book by Chevalet or Borel. So this is the Borel book. Chevalet is a Chevalet seminar, which has been it's called the Bible in SGA3, so it has been printed by Springer as part of a Chevalet collected paper, and I brought one copy to the CMI library, so it will be available here. So one has the following further. Okay, so the standing assumption is that G is a smooth affine group of our field. So the first result is the connectedness result. So if S is a torus of G, any torus, not necessarily maximal, the centralizer, its centralizer is connected. Okay, so here, I can add the further, the extra information that this group is connected. And the second result, if H is a smooth connected affine group with only one maximal torus. Then H is nilpotent, and well, then H is the direct product Okay, so if H is a smooth connected affine group with only one maximal torus T, then H is a direct product of T with some group U with U unipotent. And in particular, H is nilpotent, meaning that the descending central theory terminates. And therefore, hence, if T is a maximal torus of G, then the Cartan subgroup C of T is connected and so it's a nilpotent group and nilpotent, and more precisely, the direct product T of U with U unipotent. Okay, so this is the structure theorem for Cartan subgroups of an algebraically closed field. And of course, note since all maximal tori are conjugate, all Cartan subgroups are also conjugate. And their common dimension, and so their dimension is denoted by Grothendieck. It's called the nilpotent rank. Nilpotent rank of. Okay, so so far so good. And so these were the definitions and results of an algebraically closed field. And now let us be back where S is an arbitrarily based field. And again, G is a smooth affine S group. And now we define what what is a Cartan subgroup in general. So Cartan subgroup G is a subgroup. I wanted to is a smooth subgroup scheme of G such that for every geometric point S bar of S is a subgroup scheme C. So we want the geometric fiber is a Cartan subgroup of the geometric fiber. Okay, so I see that's the definition. And of course, Cartan subgroups I need well, also it is not clear that Cartan subgroup actually it seems as difficult to construct a Cartan subgroup of an arbitrary base as to construct a maximal torus. But in fact, Grothendieck found a way to construct Cartan subgroups. Answer for maximal torus. And so Grothendieck proof. So Grothendieck's proof is construct Cartan subgroups over infinite. Okay, so and so this is not at all obvious, of course, and there is a very beautiful idea of Grothendieck. And first, we need a definition. So let Z be a closed subgroup of G. Okay, so So we have this standing assumption that G is a smooth affine group over S. And one says Z is a reductive center of G. So what is a reductive center? If firstly Z is a central subgroup, and of multiplicative type. So it's a subgroup of multiplicative type which is central, and it is the largest one in a functorial sense. That is for every S scheme S prime, every central homomorphism from H to GS prime, where H is a group of multiplicative type over S prime. So every central homomorphism from a group of multiplicative type factors who through Z prime. Okay. And so note. So this definition is preserved by basic tension. That is, in this case, Z S prime is reductive center of G S prime. Okay, so if a reductive center exists, then okay. It's not clear that it exists, but we're going to see that this exists. And we could have said Z because, well, if it exists, it is unique. I think that, well, Grothendieck wrote A because it was not clear that this exists. So let's prove that a reductive center exists. Yes. Yes, I think so. This is a result that will occur later. Yeah. So you take the kernel of the root alpha, and yeah, and yeah, and then the kernel of alpha is the reductive center of its centralizer. This is a result that will come, which will actually come later in. Yeah. Yeah, exactly. And actually this is the key of the construction of maximal torus, because if you have a, yeah, okay, so let me spoil a little bit of thing. If you have a group which becomes nilpotent over the algebraic closure, so the unique maximal torus, and by the proposition that I'm going to write, this is a reductive center, and actually it descends to the original field. So for nilpotent groups, you are fine. And then the general proof is by induction of the dimension. And somehow the proof, so somehow the critical case is the case of a nilpotent group and one Islam. Yeah, so really, so Grothendieck understood that the crucial case is the nilpotent case, and then everything works by descent. Okay. Okay, so we have the following theorem. So let me repeat the hypothesis that G is a smooth, affine S group. And we have the following assertions. So firstly, if G admits a reductive center locally for FPQC topology. Well, so the proof will make clear what I mean by this. Then G admits a reductive center. And secondly, so a subgroup scheme Z is a reductive center if and only if it is so FPQC locally. Well, actually, 2 is contained in 1, but I just pointed. And 3, a technical result. So suppose G has connected fibers and admits a maximal torus P, then any central homomorphism U from H to G with H group of multiplicative type over S factors through so somehow we don't know if maximal tori exists, but the reductive center is going to be the intersection of all maximal tori. And it will be used to prove that the maximal tori exists. Yeah, so let me write it. So in particular, if G as reductive center Z, then Z is contained. And a last technical result. So assume S is spectrum of a field, of a field. Then G admits a reductive center Z, and further, the maximal toroid of G in bijection with those of the quotient group T prime. Okay, so let me try to prove this today. And okay, proof. So what we need to prove is that no, no, no. Oh yeah, it's normal because it's central. Yeah, it's central, in particular normal, yeah. Yeah, okay, so let me write. Hence, yeah, it's an invariant subgroup because it is central. So we can form and over a field we can form the quotient. Okay. So let's S prime to S be a covering morphism. Yeah. Covering morphism for FPQC topology. Well, so covering morphism, so it need not be FPQC, but it's a composite of a Zariski open cover, which need not be FPQC if the cover is infinite, and FPQC morphism over each open set. So and the assumption, and so we assume that such that G prime, which is G, so that the Bay change has a reductive center. Let's call it Z prime. Okay, so now as usual, we consider S double prime, which is the fiber product, and so we have the two projections P1 P2 from S double prime to S prime, and so we have the pullbacks. So we have the pullbacks G double prime I containing Z double prime I for. Okay, so we have those two objects over S prime, and so we have these two maps to S prime, and so we have we have the pullbacks by either of the projections. Since 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 G prime is coming from S, so we have a descent pattern RC, so which is an isomorphism between these two pullbacks. So this is an isomorph. So this is an isomorphism. This is an isomorphism of group schemes over S double prime. Well, because because what is this? So this is G cross S prime cross S double prime, and so here this is over P1, and so but so this identify with G cross S double prime without mentioning the choice of P1 or P2, and here the same. So these two guys are isomorphic. And now, so this one is a reductive center of the first group, and so by uniqueness of the reductive center, hence C induces an isomorphism. And so hence C induces a descent pattern on, well, a descent datum is just an isomorphism like this, and Z prime is a group of multiplicative type, hence affine over S prime. Hence, as we have seen in August, the descent datum is effective. Which means that there exists S subgroup Z of T times dot Z prime is the base change. Oops. Okay, so the reductive center assumed to exist of S prime, so it descends to a subgroup scheme of S, and so it only remains to prove that Z is a reductive center. So by descent we have a Z, and so now let us prove that this that this Z is a reductive center. Reductive center of, and so firstly, Z is of multiplicative type since since by base change it is of multiplicative type, so Z is already of multiplicative type. Uh, hmm? Yeah, and I think it's, I forgot to check this, but I think it's more or less clear. I think it's more or less clear than yeah, Z is central. Z is central because if we consider the centralizer in G of Z, so if we base change this by the functorial definition of centralizer, so this is the centralizer in G prime of Z prime. And since Z prime is central in G prime, this is G prime, which is G base change by S prime. And since S prime is faithfully flat over S, this implies that the inclusion, this implies that the inclusion of that one into G is already anequality. Okay, so it is central, and so we only have to check the universal property. Okay, so okay, so let T be any S scheme, and U from H to G to GT, a central homomorphism, with H, a multiplicative type group over T, and we want to prove that U factors through that. This is what we want to prove. So we are going to base change this. So let T prime be the base change. And so we get, and so let's make base change from T prime to T. So we get a morphism from H T prime to GT prime, which is G S prime plus over S prime T prime. And so this is U base change. So let's call this U prime. And so we know that U prime factors to Z T prime because Z prime was a reductive center of this one. Okay, so we have this factorization, and it's prime belongs to the equalizer of, so we have the morphism of T prime. So this is a morphism. It lands in this one, and so it has the same images in T double prime. Where, of course, T double prime is T prime cross T, T prime, and so this is the same as T cross over S with S double prime. Okay, and so, but this equalizer, oh, okay, and this equalizer is in fact from group from H into ZT. Because so this one is deduced from this one by the base change to S prime, and so this is because S prime to S is SP2. Okay, so okay, so this is okay, so this means that the original so this means that our original U in fact factors through ZT as wanted. Huh? So this proves Z is reductive center for G. Okay, so this is the crucial thing. And 2 is a special case because so the proof of 2 is contained in the proof of 1. Actually, the proof starts here. So if we have a Z such that the group obtained by base change is a reductive center, that Z already is a reductive center. Okay, so and so 3 and 4 we'll see it the next time. So let me mention 2 things here. So it's important to what do I want to say? Yeah, so this result, yeah, so this result is this is an important result because this proves that well there is the largest central subgroup which is of multiplicative type, and it is constructed by descent. But as you know, of a non-perfect field, there is no such thing as a, even for commutative group scheme, there is no such thing as the largest unipotent subgroup, because this does not behave well by base change. So you know that over an algebraically closed field that you have a structure theorem for algebraic group that a commutative group is a direct product of a group of multiplicative type by a unipotent group. But of a non-perfect field, and so even more of a general base, no such thing is true. But of an arbitrary field, a commutative group contains a largest subgroup of multiplicative type. Okay, and the quotient, of course, is unipotent. Okay, so you don't have a largest unipotent subgroup, but you do have a largest central group of multiplicative type. Okay, so I think it's the right time to stop here for today. And so next time I will prove a 3 and 4, and then explain a Grothendieck construction of Cartan subgroup using the theory of regular elements in the Lie algebra. Ah, yes, another thing that I can say in 5 minutes. So Grothendieck proof is beautiful because it really uses the Lie algebra and the regular elements in the Lie algebra. And there is another proof of the existence of maximal tori over an arbitrary base field, which is due to Borel and Springer, and which is reproduced in Brian Conrad course in the SGA Swiss summer school. But while some years ago I received an email from Springer giving credit to Grothendieck, and he explained, so in that email that will be published in the new edition of volume 2 of SDH3, Springer explained that after Grothendieck obtained that proof that I'm going to lecture on next time, he went to Utrecht and to visit Moore, and he gave a lecture about his proof, and Springer was in the audience, and he wrote to me that he didn't know enough of scheme theory to understand the details of the proof, but he understood that Grothendieck used crucially the Lie algebra, and this motivated him to devise his own proof, which he completed with the help of Borel a few months later. And so they have a different proof, but he wrote to me that the incentive for this proof was Grothendieck proof. So even so, there is this other proof by Borel Springer. Springer made clear to me that the very existence of that proof is due to Grothendieck talk in Utrecht. Okay, so I think it's time to stop here. Thank you.